In this video we're going to talk a little bit more about Bayes' theorem and kind of the intuition behind what's going on. The idea with Bayes' theorem, as mentioned in the previous video, was that we want to update the probability of the event B taking place. So again, we've got the prior probability B over here that we call the prior probability, and we're going to say, given some new information, given that A has taken place, now what's the probability of B? We want to be able to update that. And without getting into the mathematical details, we want this posterior probability. And the intuition behind this is that when we get information, we are able to update that probability. Not necessarily that the probability gets bigger or smaller, but we're able to revise it given new information. So a classic example of this is an old game show called Let's Make a Deal. There is a new version of this, but back in the 70s they used to have a segment on the game show where a contestant would be brought before 3 different doors, and they're told behind one of the doors is a fabulous prize, a big pile of money, or a Ferrari, or something really cool. And behind the other 2 doors there's a gag prize like a donkey. And so the contestant was given the opportunity to pick one of the doors, and let's just say they picked door number 2. And upon doing that, the game show host would open up one of the other doors and show a donkey. So come over here, and door number 2 is the initial pick. Now here's a donkey. I'm no artist, but there's the donkey. And the contestant was then given the opportunity to either stay with door number 2 or to switch to door number 1. And so I want you to think about that. What is the best strategy for winning this game? Is it to switch, your choice, or to stay with your initial choice, or does it even matter? So push pause, think about this for a little bit, and when you come back we'll talk about these different strategies. Okay, most people when they think about this think that the probability of initially picking the money is 1/3, because before they see the donkey there are 3 doors and one of them has money behind it. So if we use classical approach to probability and assume everything's equally likely, then that would be a correct assessment. Probability is 1/3 that the money is behind door number 2. If we use the law of complements, that tells us also that the probability that there's a donkey behind door number 2 is 2/3. Okay, so now is when the information becomes useful to us. The first piece of information we have is that the contestant chose door number 2. The next piece of information we have is that the game show host revealed a donkey behind door number 3. And now that we have the information, we have to be able to use that information in the correct manner in order to maximize the probability of us winning this game. Now, the wrong way to do that is to say, well, now there's only 2 doors, so there was a chance of me picking the winning the money of 1/3 with my initial pick, and now there are 2 doors, so that chance goes from 1/3 to 1/2 because there's 2 doors and money's going to be behind one of those. So we could use the same argument for the classical probability that there's 2 doors and money's behind one of them. But if we do that, we're ignoring the information that we have in the whole setup of this problem. In other words, what I'm telling you is that the probability that there's money behind door number 2 does not change even though I know there's a donkey behind door number 3. So the probability that there's money behind door number 2 is still 1/3, and the probability that the donkey is behind door number 2 is still 2/3, which means that the probability that the money is behind door number 1 at this point is now 2/3. So the best strategy is to switch. And there's one more strategy that people tend to think of, and that is to say, well, it doesn't really matter once I get to this point, and so I might flip a coin to determine which door to pick. So there's 2 doors, I'm going to flip a coin, and half the time you'll switch and half the time you won't switch in that scenario. And it turns out if you average 1/3 and 2/3, you get a half. And so it's almost like a self-fulfilling prophecy. If you stay, the probability that you're going to win is 1/3. If you randomly decide to switch by flipping a coin, the probability that you're going to win is a half. And if you switch, the probability that you're going to win is 2/3. Now, I know this is not necessarily straightforward and easy to think about, but if you want to see it in action, you can come over here. There's a link to this web page on Blackboard Learn, and I got here just by typing in "let's make a dill applet," and there's a little description of what's going on and the argument that I just made. But it's difficult for people to understand this just by talking about it, and we know that people oftentimes can learn by playing games. And so this is a simulation. This is an applet where you can come in and you can pick. Say I'm going to pick door number 2. Monty Hall shows me a donkey, and I'm telling you the best strategy is to switch. And look at that, when I switch, I won. And so this applet's going to keep track of how many times I win when I switch and when I don't switch. So in one game in which I've switched, I won 1 time. In 0 games when I switched, I won 0 times. So I'm going to play this game a few more times. Look at that. Switch and win. Switch and win. Oh, that time I didn't win. There's a nice little rhythm you get into. You click 3 times. Oops, that time I didn't switch. There we go, there's the rhythm. So on Friday night when you're bored and you want something to do and your frat party is kind of wound down, you can pull out your computer and go and play this game over and over and over again. I'm going to keep playing it, but I'm going to push pause so you don't have to watch me. Okay, so I played the games 100 times in which I switched, and I won 72 times. That's not too far off of 2/3. If I were to keep playing it, the frequentist approach to probability that we talked about earlier would show that this proportion converges to 2/3 of the time. Now I'm going to play it 100 times when I don't switch. This gets even easier because I just click a bunch of times. There's 10. There's 20. This is really fun. If you think like Xbox is fun or Wii or something like that is fun, you've got to try this. And just to show that it doesn't depend on which door I pick, I'll move over here. The original Nintendo really had something in that track and field game where you have to push the button a whole bunch of times to run down the track. And this is really good. A good workout for your fingers. So here we go. Here's our last. Click, 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 click. Okay, so in 100 games in which I did not switch, I won 29 times. So not exactly 1/3, but pretty close to 1/3. And again, if I kept going, that proportion would converge to 1/3. So the details, the mathematical details as to why that is, are actually not too difficult to understand if you think about this in terms of what's the probability that I initially pick a donkey. In other words, if I'm going to pick door number 2, what's the probability that it's a donkey? It's 2/3. Monty Hall is going to show me another donkey, so if my strategy is to switch, I'm going to win if I initially picked a donkey, and that's going to happen 2/3 of the time. And this is a good illustration of what Bayes' theorem is all about, taking into account information that we get in the form of something happened, A has happened, that just represents some information. We can now revise the probability that we're going to win. So in the next video I'll actually go through another example problem for Bayes' theorem, but this is all I've got for this video.